Okay, I think we'll get started on this lecture. I think everyone's back from lunch, but we can make a start anyway. So we've got another EPI lecture. This one's going to be looking at a model including environmental transmission, which is a bit different to what we've been talking about so far. So far we've been talking a lot about things where you've got to come into contact with another person, or an animal's got to get into contact with another animal for transmission to occur. This case of transmission means that you have to come into contact with an environment that is contaminated in order to pick up an infection. So it's a bit different. We've also got a bit more on the next generation matrix. So we're going to go through step by step how you'd calculate it for this model. There's a couple of handouts that you'll find in that zip folder. Don't worry about them now. But one of those is just so you can try doing the same steps but for a one infectious state model, like the ones we've seen before. And then the other handout is just a bit of theory. Okay. So why are we interested in looking at environmental transmission? Well, it's an important consideration for a lot of diseases. We're going to be looking at a particular model for cholera. We model the system as having two populations, one for the humans and one for the environmental pathogen. So it's a bit strange when we think about an environmental pathogen as an infectious individual, but that's how we're going to treat it for this. And as I said, one key example of this is for cholera. So what's the idea behind the transmission? Well, if we've got our susceptible, infected, and recovered people, then a susceptible person comes into contact with some contaminated environment, and then they become infected through that contact. So it's not necessarily human to human, it's through this environmental reservoir. Once they're infected, they then shed the pathogen, the bacteria, into that contaminated environment, and so on. And then finally, we've got the recovered state, just the same as before. Okay, so that's the thinking behind it. What does it look like in terms of equations? Well, these are taken from this publication, which is worth a look. It's quite a nice read. I'm going to use the same notation that they used in that paper, so that if you look between the slides and the paper, they make sense. It's a little bit different to some of the notation that we've used previously. So for example, rather than having N to represent the total population size, here we've got H. But let's look at the diagram first. So we've got our S, I, and R compartments in the human population. That's exactly the same, but we've got this extra compartment. So again, solving problems by adding an extra compartment. And this represents the bacteria in the environment. So bacteria because we're thinking about cholera, but if you were thinking about something else, maybe you'd call it something else. Okay. So I'm going to go through all of the parts of this model before we start doing anything with it. First up is the transmission term, which has this fraction here, b over k plus b. So maybe let's look at that first. So what's this saying in the model? Well, this is the probability of infection per contact with a contaminated reservoir. So given that you come into contact with the environment where the bacteria are, this is your probability of infection. What does it look like? Well, as we look at different concentrations of cholera, so number of bacteria per milliliter, and as that concentration increases, easier to see on this screen, your probability of catching cholera given you come into contact with the environment increases, but not linearly. We've got a slow increase initially, then it ramps up, and then it approaches 1. So we've got a logistic dose-response curve for the probability of infection given contact. Okay. So let's go through some of the other things going on in this model before we start using it, especially as some of the notation is a bit different to some of the other SIR models that we've shown so far. Here, we've got N as our human birth and death rates. We've got A, which is the rate of exposure to the contaminated reservoir environment. Here it's contaminated water. We've got K here. So this is not carrying capacity in this model. It is the concentration of bacteria in the water that yields a 50% chance of infection. So you imagine if B was equal to K, we'd have K over K plus K. We'd have half as our probability of infection. Okay. What else have we got? Well, we've got R as our recovery rate. So in some of the models we've seen so far, that's been gamma. So just making sure that we've got the new parameters in mind. We've got this NB, which is the net growth rate of bacteria in the environment. So you'll see in this equation for the bacteria, it features here and we've got a negative sign. So they're assuming that without any sort of other effects, the bacteria in the environment would decline. So if we think about this, we've got no shedding into the environment. There we've got exponential decay of the bacteria in the environment. Okay. And then the final parameter we've got in this model is the contribution of each infected person to the population of bacteria in the environment. So this is shedding bacteria into the contaminated environment. Okay. Sorry? Recovery rate here. Yeah.
I thought there was an SIR.
Yes. So in this paper, and you'll see it in a few other papers as well, the R compartment is not very interesting, so they just leave it out. But let's have a think about what it would be. We've only got our recovered class featuring, so in between here, and the only... Yeah, exactly. Yeah, but it's a great point because they're still assuming that our human population is S plus I plus R. They're just not putting the R compartment up because it's not as interesting. But no, it's a good point. Cool. Okay. Yeah. Oh, H is what we had as capital N in the other models. So H is the size of the human population. So if we look at this term, they're saying that everyone contributes to the birth rate, and when people are born, they're born susceptible. And then they've assumed that the human birth and death rates are equal. So they've also got this term minus S in here because they've got mortality, so background mortality going on as well. Okay. Great. So let's go back. Now we've got a good feel for what this parameter K is meant to be. Let's go back to looking at that B over K plus B transmission probability. Ooh. Okay. So as we said, this is the probability of infection per contact with a contaminated reservoir. It's a bit odd because when we talk about B, this variable B, this is pathogens per volume. So it's a concentration. Here we've got concentration across the bottom. So we could rewrite this as pathogens divided by volume as a concentration. So one question you can ask before even getting too much into the disease dynamics is, if we think about just this term on its own, how will this change as the volume of that environmental reservoir changes? So if you think about cholera being shed into a water source, if the volume of that water source changes, but the number of pathogens in the water source does not, how is that going to affect our probability of infection? And this is one of the things that they looked at in this paper because, hopefully you can see, they had this figure. So each of these curves is a reported number of cases of cholera in the Brazilian Central Amazon region. And they've split this figure by months along the x-axis, and they've split it also by water levels. So here we've got falling water, here we've got our lowest water level, and here we've got rising kind of water volume, and then the highest water level. And each of these curves is just a different year that they were looking at. So the reason that is interesting is because if we think about these falling waters in terms of the volume of our environmental reservoir, here our volume is declining. Then around, I think, November, we reach our lowest water level, so our lowest volume. And then we can see that that corresponds to an increase in the number of reported cholera cases until waters start to rise again, and this is already declining in the number of reported cases until we reach our highest water level here. Okay. So we've got seasonality in the volume of the environmental reservoir, and that seems to have some relationship with our reported cholera cases. So what's going on? Hopefully, no. When we think about how this translates to our probability of infection, and this is where I would sketch it on a whiteboard, but let's imagine that we've substituted P over V in all of these places and then rearranged. So you might want to look at this a bit separately. But if we think about pathogens per volume, we put this value in everywhere B appears. We end up with volume only being present on the bottom of this fraction once we've rearranged. So what that means is, when we think about the volume of our reservoir, if our volume is small, but we've got the same number of pathogens in the environment, the concentration that you'd experience if you came into that contact with that contaminated environment is higher. So when we think about the logistic dose response curve, if we've got a more concentrated kind of contamination, that increases our risk of infection if we come into contact with it. So even though often flooding or things like that are associated with cholera outbreaks, a more concentrated, contaminated environment can lead to a higher risk of transmission. And that's what we're seeing with this. Okay. So we've got our model all set up here. This model, even though it's a little bit weird, we've got two infectious classes. So we've got our infected humans, and we've got this bacteria kind of environment compartment. So given that we've got sort of two infectious classes, that means that we've got a structured model, and in order to calculate R0, we would have to use the next generation matrix approach. So this is just as we've seen before, but rather than adults and children in a human population, now we've got infected humans and the concentration of bacteria in the environment. The process that we're going to use is going to work for this. It will work for age structure. It will work for if you're splitting by sex or different populations. The same process we're going to go through should apply to any sort of structured model like this. Okay.
Just come back a bit on why we should use the next generation matrix.
Okay. So let's go back here. So in the other model that we saw, the next generation matrix approach, what we had was two populations, adults and children, and both of those populations had an infected group. We've got a similar sort of idea here. We've got two populations. We've got humans and the bacteria in the environment, and each one of those has got an infected group. So we've got infected humans, and then we've got this concentration of bacteria in the environment. So as soon as we've got more than one infectious state, that's when we start needing to have this next generation matrix. Because it's not necessarily, we've got kind of infected humans producing bacteria and contaminated in the contaminated environment, and we've got bacteria leading to a risk of infection in humans. So there's kind of two routes there. What are we going to be thinking about with this? Well, so we're thinking about the R0, basic reproduction number. So if you imagine someone is born in their lifespan or generation, through their life, maybe they have children through births and then they die. We're thinking about the same sort of process with this infected person or this infectious state. So something is infected, or someone, over the course of their infectious lifespan or generation, they produce 3 more infections. They infect 3 more people. We've got contribution of bacteria into the environment. And then they recover or die. So with the basic reproduction number, we're always thinking about what does this look like if the entire population is susceptible? What is the potential of that one infected person or bacteria to go on to infect others if everyone is susceptible? Okay. So we're thinking infections per generation and in an entirely susceptible population. So this is our definition of R0, infections per generation and an entirely susceptible population. It gets a bit weird for environmentally transmitted diseases because when we say infection, we could mean humans or shedding bacteria into the environment. And like we spoke about before when you're talking about adults and children and taking the average of those two, here with the R0, we're taking an average between our infectious states, our humans, and in bacteria. So it gets a bit weird. Okay, so I'm going to step through how we're going to come up with the next generation matrix, how we calculate R0, which you've already seen a bit. That's where we get to use our eigenvalues. And then I'm going to come back to the next generation matrix and see if it can do anything else for us, because it can. If you're interested in seeing a few more examples of this paper is quite helpful. It's got examples for susceptible, exposed, infected, recovered models, and a couple of other examples as well. And it's using the same sort of steps that we're going to go through now. So if you want to read more, this is a good paper for it. Okay. So, big idea, infections per generation. And we know we've got a structured model, so we need to think about infected humans and bacteria. So, step 1. Firstly, infections per generation. We're going to slightly rephrase that as transmission events. So an infection occurs when transmission occurs, divided by transition. So where does that come from? If you remember in the one population model, our SIR model, when we first looked at R0, the value was beta over gamma, right? And why was that? So the expected time an infected person stays infected was 1 over gamma. But gamma was our recovery rate. Gamma was a transition rate there. So this is capturing that we've got a transmission event, which in the previous one was beta, and it's times 1 over transmission, so the average time that someone is infected for. That's just where this comes from. Okay. So, first step on putting together our next generation matrix is to see how our infectious differential equations changes with respect to each infectious variable. Again, we want to know when we're going to see a transmission event, and that depends on other infected compartments, and we want to know when we're going to transition out of the infected groups. This is where I was very careful on the differential equation lecture and said that we only come across partial derivatives a couple of times. This is one of them. But what are we doing? Okay, so we've got a little bit of slightly different notation here. We've got these curly Ds. That's all, that's only suggesting that we're doing partial differentiation. But what are we really doing here? We're doing exactly the same thing that we did with our other differentiation. We are asking, how does this equation here change with respect to a change in I. Okay? So we're differentiating this equation with respect to I. Because in this first term, we've got no I, everything disappears. In the second term, we've got R times I. So when we differentiate that, we just get minus R. Okay. Everyone happy so far? Okay. Is it partial differentiation or the next generation matrix so far? If it's partial differentiation, don't worry. Imagine it is just differentiation, but with a slightly different variable. Okay. Okay, I'm going to keep going. Don't worry. We're going to go through each of these bits and bobs. But what's the main idea behind this? We want to know how our system of infectious differential equations changes as each of our infectious variables changes. That's the main idea. The route to get at that is partial differentiation, but the main idea is we want to know if you increased I by 1, what happens to this rate? If we increased I by 1 here, how does that change the rate here, the differential here? Okay. So, I have differentiated my I compartment equation with respect to I. I can do the same with respect to B. So it's a bit more messy. I differentiate this with respect to B. I'm not going to go through all of the steps. You might want to trust me. You might want to try it in Wolfram. So if we take this, we know that B only appears in this part of the equation. No B here, so that disappears. So we're just differentiating this part. We do it in a couple of steps. I'm not going to go through it. But essentially, this gives us how is this differential equation, how is this di by dt changing if we change B? That's what it's giving us. Okay. Let's go on to the other equation. It's a bit nicer. So if we look at this equation now, we can say, how is this equation going to change if I increase I by 1? Okay. I only appears here. We differentiate EI with respect to I. We just end up with E. Okay. We can do the same thing for B. Again, B only appears in this term. So we differentiate minus NBB with respect to B. We just end up with this constant. So this tells us if we increased the number of infected people by 1, our rate of growth over time of the bacteria compartment would increase by E. Yeah?
Yes.
And this is telling us if we increased our number of our concentration of bacteria by 1, it would change the rate, or dB by dt, by minus NB. That's what we've done with the partial derivatives, just thinking about how does this equation change if I change either I or B. Okay. That is the end of the partial differentiation. Sorry?
In the previous one.
Yeah?
So the I should be constant.
Ah, we're coming back to that. So that was step 1, was doing the differentiation. So how do these infectious compartments change if we change either I or B? Step 2, we substitute the variables in at disease-free equilibrium. So why are we doing that? Well, if we go back to the definition of R0, it's the expected number of secondary infections in a completely susceptible population. That's why we say at disease-free equilibrium, because at this equilibrium, everyone's susceptible. S is equal to the size of the total population. Okay. So because we want to capture the dynamics at this special point, at the very beginning of an outbreak or an epidemic, we substitute these variables in. So where do they appear? Well, they only appear in this term. So here we've got B and S. Okay. So at disease-free equilibrium, everyone's susceptible. So S is equal to the total population size of the human population. And B, well, we've got no bacteria in the environment yet. So B is just 0. These are the values of these variables at this equilibrium point. Okay. So we substitute those in, and we get this. This is giving us how these equations are going to change if our I or B change, our infected humans or our bacteria change, at this special point in time, at this disease-free equilibrium. So if you think about this, is giving us the very beginning of that exponential growth, the beginning of an epidemic. Okay. Step 3. We split these kind of terms into those that describe transmission, so when a new infected human comes about or a new bacteria is shed into the environment, and transition terms, so where someone recovers or a bacteria dies or decays in the environment. So we split them up. Firstly, transmission terms. Here, we've got E. That was the rate that bacteria is shed into the environment. So if someone's infected, they shed bacteria at rate E. Okay. Over here, we've got a transmission where we've got a new infected human coming about. So this is A, the rate they come into contact with the environmental reservoir, and then H over K, some measure of the probability of infection given contact. Okay. So those are our transmission terms, new infected states. Transition terms are when people recover or when the bacteria decay in the environment. Okay, so these are the rates that describe leaving the infected compartments. Okay, so we split them into 2 different types of terms. We can tidy that up into a matrix. So as you can imagine, here we've got an infected person shedding bacteria into the environment. So that increases B by rate E, and vice versa. So bacteria increases the risk of an infection in humans. Okay, we've got our transmission matrix. We can do the same for our transition matrix. So on the diagonal, infected humans recover, so it's times I, and bacteria decay in the environment this time. Last bit, almost. We can put this together to make the next generation matrix. So if you look at that paper that I cited earlier, this is how they write it. So what they're saying here, well, we've got our transmission matrix, capital T, and here we've got our transition matrix, capital sigma. So we've got a bit of matrix multiplication, inverse. This is the point where I would very carefully make sure that I've got all my values calculated correctly, and then I'd get a computer to do the nice rearranging bit. But we're going to step through it briefly. So here, what I've done is I've taken my equation, my transmission and transition matrices, and I've just put them in exactly the same. So for this particular model, this is what we get. If I take the inverse of this matrix, it's nice, it's a diagonal one, so we just get 1 over both of these. If you remember back to that one population SIR model, 1 over the recovery rate is the expected time in the infected compartment. So this is hopefully looking a bit familiar. And now we've got to multiply our matrices together, again, to get a computer to do the heavy lifting, but essentially you do along the row and down the column. If you don't want to do this, I don't blame you. So we're multiplying this row by this column, and so on. Same in this, easier to see over here. So we do our matrix multiplication, and we end up with our next generation matrix. I'm going to tidy up the minus sign. This is my final step. And there we go. So we've got our next generation matrix. As we've seen earlier, if you take the lead eigenvalue of this matrix, that will give you your R0. So what does that look like? R0 is the largest eigenvalue of the next generation matrix. Without getting into talking about eigenvalues and eigenvectors again, we can think about as R0 is the kind of dominant behavior. If we kept applying our next generation matrix to our vector of infectious states, this is the sort of average behavior that we'd see in terms of the number of new infections per generation. It's a bit odd though, right? So here we're talking about R0. It's the expected number of new infections. An infection in this model can be an infected human, or it can be an increase in the concentration of bacteria in the environment. It's still an extremely useful quantity because it gives us an idea of if our epidemic is going to naturally die out or start to grow. So it's still worth calculating. But if we only stopped here, we'd be missing some of the information that we've worked so hard to get from the next generation matrix. So let's go back to it. If we've got this, we've got quite a lot of information. So if we think about what it's telling us, we've got infected I and B here. So one bacterial unit or an increase in the bacterial concentration leads to this many new human infections. Similarly, one new infected human causes this many bacterial units to be created. Let's look at this one, it's a bit nicer to work with. E is the shedding rate into the environment. In the old models, that would be a bit like your beta. This is your transmission events. And then we do 1 over R, because R is our recovery rate. That would be like our 1 over gamma. So this looks a lot like the old R0 equation that we had before. So as I said, we worked hard to get this. Can we use it for anything else? We've got a bit of insight here. This is how one infected class affects another one. But it might be useful to know which one of these is contributing more to our value of R0. So if we're thinking about control, we've worked out our R0 and we found that it's greater than 1. Oh no, we're going to have an epidemic. We might like to think, okay, well, we've got 2 infectious states. Which one do we target for an intervention? It'd be good to know which one is contributing more to that value of R0 that's greater than 1, because we want to be quite efficient with what we do. So we've calculated our next generation matrix. We're going to make it work for us. We can use it to decompose R0, and that gives us what proportion of R0 is due to the bacteria and what proportion is due to the infected humans. We're going to do it using this sum unit eigenvector. Don't worry, there's also a handout on this explaining how you calculate it. And we're also going to use the, corresponding to the largest eigenvalue. And we're also going to use the sum of the columns of the next generation matrix. If we put all of that together, it will give us the individual contribution of each infectious state to our value of R0. Well, let's do it. Okay, so we get our lead eigenvector of the next generation matrix. As Andrew mentioned earlier, this is the distribution corresponding to that lead eigenvalue. So we've got a structured population. Not only do we have the magnitude of new infections per generation, but we've got where they're distributed in that population. We divide through by the sum of these elements. That just means that if we've got this, which looks horrible, I appreciate, if we add up these terms, they add up to 1. So now we've got a proportion of our distribution in each state. corresponding to our lead eigenvalue. Okay. I mentioned that we're going to need the column sums. What do they mean? Well, if we've got an infected human, it contributes 0 new infected humans. We've got 0 there. And E over R, new bacteria per generation. Okay. And if I've got a bacteria, it's going to contribute this many new infected humans in a generation and 0 new bacteria. Okay. So those are our column sums. So we've got the magnitude of new infections produced by both infectious state. We've got the distribution from that sum unit eigenvector. We put it together, we end up with this mess. And I know you might be thinking, why would we go through all of this? So I think better described by a figure. So here is a figure of this particular model. I've taken different values of 2 parameters, E and A, and put them into that model. And I've calculated R0, and I've set it at 1.2. So for every pair of values here of our parameters, we get the same R0. So if we created our model of cholera and we put it all together, we got our next generation matrix and we calculated our noughts, we'd end up with 1.2. But then if someone said, okay, well, it's greater than 1, we're going to have to think about an intervention. What should we target, whether we should target infected humans or the bacteria in the environment? Depending on these pairs of parameters, different strategies might be more appropriate. Over on the left, for a low value of A, low amount of contact with the contaminated reservoir, but a high shed rate into the contaminated reservoir, most of the contribution to R0, this kind of turquoise colour, is coming from the infected humans. If we go over here, we've got a very high contact with the contaminated reservoir, but a low shed rate into the environment. Most of this contribution is coming from bacteria. So this suggests that even for the same R0, for a model that we've put together and we've calculated our next generation matrix, we might have slightly different interventions that we'd want to use, just because of the particular parameters we might be exploring. Okay. So we've had a look at the environmentally transmitted disease model. Again, the paper's quite nice, it's worth a read. Even before we get onto the differential equations, because of the way that the transmission term is set up, we get some nice results around the volume of the environment and how that might affect our infectious disease risk. Because it's got more than one infectious state in the model, we need to use a next generation matrix approach to calculate R0. But that can tell us a lot more than just R0. So we can play around with it, we can think about which infectious state is contributing more, and that might affect how we do our interventions with it. Okay. Any questions on any of that? This is the last time partial differentiation ever comes up in this course, right? Yep.
If you can just explain briefly again how each component in the next generation, like what we ended up getting, the interpretation of it.
Sure.
Sorry, no one has.
This part.
Yes.
So the question was, can we just go through this a bit more and think about what the next generation matrix is telling us? So let's ignore everything but this part, this E over R. The reason I'm saying this part is because when we had our SIR model and we calculated R0, it was beta over gamma. So what is that saying? Well, we're always thinking about the number of infections per generation. Number of infections is our kind of effective transmission rate. In the other model, it was the beta term. Here, it's E. E is the rate that someone who's infected, a person is infected, contributes new bacteria to the contaminated environment. This rate is their rate of new infections of bacteria. We do 1 over R because in the model equations we set up R as our recovery rate. So 1 over R, assuming an exponentially distributed infectious period, gives us the average amount of time that someone stays infected for. So 1 over R is our generation time. So we've got E, R infections per generation. So this looks a lot like what we had before, it's nice. This is a bit more horrible, but it's the same idea. So again, we're thinking the number of, if we've got a bacteria in the environment, we're thinking about the number of new infected humans that that's going to lead to per generation. So the infected humans is all of this. So we've got our rate that infected humans come into contact with a contaminated reservoir. We've got some measure of that probability of infection given contact, so related to the infectious dose. So that's our new transmission, our new infections. And then we want the per generation, so that's where we've got this part. So 1 over NB gives us the average amount of time that bacteria stays in the bacteria compartment. So this gives us our infected new humans per generation. So each of these terms will be giving us the new infections of that particular type per generation of that particular type.
So does that, if I'm understanding it, is it more like a cross
Yes,
infection kind of
exactly.
from bacteria to human and then
Yeah. We've got no human-to-human infection, and we've got no bacteria-to-bacteria infection. Okay. Any other questions on this? Okay. Okay. I think we've got a brief practical coming up, and then we've got a coffee break before your seminar. So with the practical, it's going back to probability. Andrew, I don't know if you want to talk a bit on that practical, or whether we just have a break.
Let's have a quick break.
Yeah, I think so. Okay, let's have a quick break before diving into any more practical and just move around a bit. And if you've got any more questions, feel free to throw them my way.